Welcome to the second unit in antenna and microwave engineering. In second unit, we will be seeing radiation mechanism and design aspects. Now, this is the syllabus in the second unit. In the second unit, we are going to see about the various radiation mechanisms of various antennas and the design aspects. So, in that we have a radiation mechanism of linear wire and loop antennas, aperture antennas, reflector antennas, microstrip antennas, and frequency independent antennas, and its design, considerations, and application. So the main objective of this particular unit is to understand when the radiation takes place in antenna, to understand the radiation mechanisms of antenna, to understand design considerations of antenna, and to understand the various applications of antenna. Now, what is radiation mechanism? Radiation mechanism means propagation of electromagnetic wave from the antenna and the receiver electromagnetic waves to the antenna. Now, the antenna functionality mainly depends on the radiation of transmission line. Now, whether a single wire radiates power. Now, if you can see the answer for that, a transmission line conducting current with an uniform velocity, and the line being a straight one with infinite extent radiates no power. That means a transmission line which has an uniform velocity of current which is flowing in it will not radiate any power. Now, when a single wire can act as an antenna, is that the conducting wire radiates electromagnetic energy if there is an oscillating current in the wire and the steady current in curved, bent, discontinuous, terminated, or truncated wire. So these are the two conditions where uh, the radiation will occur in a single wire. So the first condition is that in the wire there should be some oscillating in the current, and if the current is the steady current in the wire, then the wire should be like a bent curve or a curved curve, or it should be like a discontinuous one. Then only the single wire radiates. Now these are the various figures where we have the radiation being occurred in a single wire. Now if we have a wire and in that if we have a sinusoidal signal being given, right, uh, now this straight line will radiate the electromagnetic field. And similarly here if we give only the DC voltage, the steady current if we give, then if we make the wire as an curved one, then it will radiate, and if we bend also it will radiate. That means there will be change in the velocity of the current, thereby it radiates. And then this continuous wire, in the sense that there are two different diameters of the wire being connected, and even that radiates. Okay, and the truncated wire in the sense that it is been now in this particular figure you can see that the wire has been truncated at the end, it has been cut at the end, and another wire where the wire is grounded. Right, now wherever we have some change in the current flow in a conducting material, in that places the radiation will occur. Now whether the radiation will occur in two wires. Now this is a condition. Now if wavelength is lambda, that is we have a transmitter which is generating the frequency, and let the wavelength of that will be as lambda, and then the distance between the two wires is d. If the distance between the two wires is very much less than the wavelength of the signal, then no radiation will occur, right? That is one condition. Now when does the wire, that is when does the two wires will transmit the power, or when the two wires can radiate, is that now whenever the two wires are very close to each other, when the distance between the two wires d is very much less than the wavelength, then it will not radiate. So we increase the distance between the two wires, then what happened, the electromagnetic field get exhibited, and this place is called as the tapered transition, and where we have the electrical field present. And from this, now this is an generator, this is a two wire line, and here in order to have the electromagnetic field generation, we tapered the transition session where electromagnetic fields will be generated and through which the radiation occurs between the two wires. So as the value of D is very much greater than lambda, we will be having an excellent radiation between the two wires. Now in this we are going to see the linear. In the second unit we are going to see about the linear wire antennas. In linear wire antennas we are having about five different types of antennas, where we are going to see the infinitesimal dipole, small dipole, region separation, and then finite length dipole, half wavelength dipole. Okay, now now what we do is that we are going to learn about how the radiations will be, and we are going to see how the radiations can be measured. Okay, now quickly just go with that. Now considering with the radiation, now the ultimate aim in the second unit is to find out the radiation fields, right? So in order to find out the radiation field, this is the main block diagram to find out the electric and magnetic fields right from the antenna. Now this is the figure. If we can able to understand the figure, we can able to calculate the electrical field and the magnetic field, right? So what we have to do, so consider we are having a source with electric current density J and magnetic current density M. Then if we can integrate the electric current density and the magnetic current density, we can able to get the electrical field intensity and the magnetic field intensity. So our ultimate aim is to get the electric field intensity and magnetic field intensity, right? This is one part. This is the one part, and the second part is that we have the J and M, and we integrate, right? Integrate, and we get the vector potentials, right? So the vector potential, that is the magnetic vector potential and the electric vector potential. From that we can differentiate. So integration and differentiation path we have. If we can differentiate the magnetic vector and electric vector potential, we get the electric field intensity and magnetic field intensity. Now this is the main structure. This is the entire second unit, the process which we do, right? For that we need some basics of the spherical coordinate system, and then these are the equations by which we can able to calculate uh, the value of that is the value of the vector uh, magnetic vector potentials. So this is the second part, and just we are discussing now in order to find out the. So we are going with the second path, right? So if J, that is the electric current density, and M, magnetic current density, is given, we go and we find out, we integrate it, and we calculate the value of A and F, and then we find the value of E and H. So here we have the formula for A and F. So we use these formulas to calculate the magnetic and electric vector potentials. Okay, and then we calculate, and then later, yeah, and then we calculate the magnetic fields. Okay, now fine, and now this will be done for an infinitesimal dipole. Okay, and then we do with, now these are the equations for the infinitesimal dipole, right? And then we do some mathematical stuff to find out the value, that is electrical field intensity and the magnetic field intensity. Okay, and then so similarly we do all these calculations. That is, for the calculations we do is we do all the calculations to calculate the E bar and H bar field, that is the electric field and the magnetic field, and even we try to get the power dissipation and the radiation resistance, right, emitting out of all the antennas which we have seen at the starting. That is, we are going to find out the we are going to find out the magnetic field intensity and the we are going to find out all the magnetic field intensity and the electric field intensity of all these antennas in the second unit. Now this is the gist of the second unit. Okay, thank you for listening to this video. Hope we will see in very deep where we can see the radiation mechanism and the design considerations of all antennas in further class, in the further video lecture. Thank you for listening. Thank you.